Hello, good day, sir. My name is Gian Sibayan, and today, along with my project partner, Lance Santos, we'll be walking you through our final course project, where we investigate a real world dataset to extract business insights using clustering, association rules, and a look at reinforcement learning. So, firstly, our entire analysis is built on the online retail to UCI dataset, which we source from Kaggle. This is a fantastic dataset because it contains 2 years of real transaction data from a UK-based online giftware retailer selling to customers across multiple countries. And we chose this because it's rich with transaction and customer level data, making it perfect for the two main tasks we wanted to tackle, which is market basket analysis and customer segmentation. And this dataset, it did have some weaknesses that we needed to address, like canceled transactions and some missing data, which we'll cover next. So first, we loaded the libraries. We used standard data science tools like Pandas for data manipulation, Matplotlib, and Seaborn for visualizations, and scikit-learn for our machine learning models. And as we loaded the dataset, we get our first look at its structure. It includes columns like invoice, stock code, quantity, price, and customer ID. So our initial inspection revealed that we were working with over 1 million transactions using the info command, and we found that two columns had missing values. These are description and, more importantly, customer ID. The customer ID was missing almost 23% of its values, which is significant for customer level analysis. And the descriptive statistics also showed some potential issues like negative values in the quantity and price columns, which shouldn't be possible for a sale. Our first cleaning step was to handle duplicates, and we found and removed over 34,000 duplicate rows, which you can see confirmed in our output. And next, we visualized the missing data using the Missing No library. And this bar chart shows us a clear picture of the large gap in the customer ID column compared to others. Now for the main data cleaning, first we removed all canceled orders. Those are transactions where the invoice number starts with a C, which took out over 19,000 rows. Then we filtered out any rows where the quantity or price was 0 or negative, and this removed another 6,000 invalid entries. This left us with a clean dataset representing only valid, complete purchases. Now with clean data, we started feature engineering. For our clustering analysis, we aggregated the data by customer, and we calculated each customer's total number of orders, total items purchased, and total spending. Because clustering algorithms are sensitive to the scale of data, we then standardized these features using scikit-learn's standard scaler. Now for our market basket analysis, we transformed the data into a basket format, creating a matrix where each row is an invoice and columns are products, with a 1 if the item was bought and 0 if otherwise. Now we're moving on to part B, customer segmentation. Our goal here was to group similar customers together, and we researched several algorithms according to the instructions, like dbScan and hierarchical clustering, but we chose k-means because it is fast, easy to interpret, and works extremely well with the kind of scale numerical data we prepared, making it a practical choice for this retail context. So first, to determine the right number of clusters, we use the elbow method shown here, and we plot the model's performance for different numbers of clusters and look for the elbow where the curve starts to flatten. And as you can see, there's a clear bend between 4 and 5 clusters to suggest that 4 or 5 is the optimal number of segments. So we tried 4 or 5, and even 6 and 3, but 4 was showed the best cluster for us. So we proceeded with 4 clusters to ensure the segments were distinct. Next, we evaluated our clusters using 2 key metrics, the silhouette score and the Davies-Bouldin index. Our silhouette score showed 0.51, which indicates that the clusters are fairly well separated. Meanwhile, the Davies-Bouldin index showed 0.84, which suggests that the clusters are compact and distinct. And it's important to note that we can't use metrics like accuracy here because clustering is unsupervised, so we don't have pre-existing correct labels to compare against. And to visualize these clusters, we used PCA to plot them in 2D. This scatter plot on here clearly shows our 4 customer segments. So now notice how cluster 3 in pink is very distinct and separated from the others, suggesting a unique customer profile. And then, what do these clusters mean? So we profiled them based on their purchasing behavior. So cluster 1 is our star segment. It's the high value and high frequency customers. We have the highest number of orders and by far the highest total spend. Then we have cluster 2, which represents our mid-level regular buyers. They are reliable, engaged customers with good spending habits. And then we have clusters 0 and 3, or our low activity, low spend customers. They are likely occasional or one-time buyers who could be re-engaged with targeted marketing. And that's it for clustering. So now we are in part C for our market basket analysis, and we have to answer the question, what products are frequently bought together? So we use the a priori algorithm, which is popular because it's straightforward and effective at generating explainable if-then rules from transaction data. Now, after running a priori, we generated association rules, which you can see in the table. So let's break down the metrics for our top rule. If a customer buys a pink Regency teacup, they are likely to also buy a green Regency teacup. So the support is about 2.1%, which means this combination appears in 2.1% of all transactions. Confidence is 83.4%, which means that when someone buys the pink teacup, there's an 83.4% chance that they also bought the green one. Most importantly, the lift is almost 25, and lift value greater than 1 indicates a significant relationship, so 25 tells us these items are purchased together 25 times more often than we'd expect by random chance. Now, this scatter plot visualizes all of our rules. The large, bright yellow bubbles represent rules with high lift and high confidence, and these are our strongest, most actionable insights. And based on these, we developed 5 actionable recommendations. So for example, we suggest bundling the white hanging heart tea light holder with the Regency cake stand treater as a themed package. And for 2 different jumbo bags that are often bought together, we recommend promoting them as stylish storage solutions. That's all for part C, and moving on to part D and E, Lands. So now we're in part D, where we explored reinforcement learning. And it is fundamentally different from supervised or unsupervised learning because it involves an agent learning through trial and error by interacting with an environment and receiving rewards or penalties for its actions. Now, to illustrate this, we created a hypothetical smart shelf-stocking agent for a retail store. And the state would be the current inventory levels and recent sales data. The action would be how many units of each product were stocked. And the reward would be based on maximizing profit from sales while minimizing costs from wasted products. So now let's walk through exactly how our hypothetical smart shelf-stocking agent would learn step by step. So the first is initialization. First, the agent starts with a blank state, an empty or randomly filled queue table. And at this point, it has no knowledge about which restocking actions are good or bad. And then it will be observing the state. So each day, the agent begins by observing the current state of the environment. This includes the inventory levels for each product, the sales data from the previous day, and the day of the week. And then third is the selecting an action, if either exploration or exploitation. And this is a critical step where the agent must decide whether to exploit its existing knowledge or explore new possibilities. And this uses an EGD strategy. Now, most of the time, with high probability, it will exploit what it really knows by choosing the action that its queue table says will lead to the best reward. But occasionally, with a small probability, it will explore by choosing a completely random action. This exploration is essential for discovering new and potentially better strategies it would never have tried otherwise. And then after that step is taking action and observing the outcome. The agent takes its chosen restocking action, then a stimulated sales day occurs. The agent then observes the outcome. If it's a reward or from profit from sales minus the penalty for waste, and the new state of the inventory for the next day. Step is updating the queue table. This is where the learning happens. So the agent uses the reward it just received and the new state to update its queue table using the queue learning formula. This update refines its understanding of the long-term value of taking a specific action in a specific state, and it's learning directly from the consequences of its decisions. And then, final step is repeating over time. So this entire cycle repeats for thousands of simulated days. With each iteration, the agent's queue table becomes more and more accurate, and it learns the nuances of demand such as peak and surges and finds a strategy to stock just enough of each item. Ultimately, this will develop an optimal policy that increases profit and operational efficiency. Now, while reinforcement learning offers huge benefits like continuous learning and hyper-personalization, it comes with challenges because it requires massive amounts of data and a carefully designed reward function and significant computational power to train effectively. So, in conclusion, this project demonstrated an end-to-end data science workflow. So we took raw data, cleaned it, segmented customers into meaningful groups, discovered powerful product associations, and explored the future potential of AI with reinforcement learning. So these are the techniques that allow modern retailers to move beyond just selling and toward truly understanding their customers, making smart, data-driven decisions. So now we're in part A, which is the final section of our project, where we will discuss our findings, our conclusions, and provide actionable recommendations. So first, let's recap our journey. In Part A, we addressed data acquisition and pre-processing, and we carefully selected the online retail 2 dataset because it's suitable for both clustering and association rule mining. And then we performed a thorough data overview, checking for quality issues like missing values and duplicates. And a crucial step was scaling our numerical features to ensure our clustering model wasn't biased. And for market basket analysis, we transformed the data into a basket format, representing each transaction as a list of purchased items. And then in Part B, we focused on customer segmentation. We researched several clustering algorithms and justified our choice of k-means because it works well with large-scale numerical data. And then we used the elbow method to determine that 4 or 5 customer groups would be most effective. Now, after applying the model, we explained why supervised metrics like accuracy are unsuitable for this unsupervised tasks and instead use metrics like the silhouette score. And finally, we profiled each customer segment and giving us a practical insight into the different types of the customers that the business serves. Now, in Part C, we conducted our market basket analysis. First, we compared the a priori algorithm to others like ECLAT, highlighting why a priori is a common choice. And then we emphasized the importance of the lift metric, explaining that a value greater than 1 signifies a strong, non-random connection between products. From this, we identified at least 5 actionable association rules, detailing how they could be used for product bundling or cross-selling. In Part D, we provided a conceptual demonstration of reinforcement learning. First, we explained how reinforcement learning is fundamentally different from supervised and unsupervised learning because it involves an agent learning through trial and error with reward feedback. We then defined the state space, action space, and reward function for our hypothetical smart self-stalking agent. Then we walked through how this agent would learn over time and discuss both the powerful benefits and the practical challenges of applying reinforcement learning in a real retail setting. Now we are in the additional discussion for the results. So let's dive deeper into the insights of our 2 main analysis. So our customer clustering successfully sorted customers into 4 distinct groups. We identified Cluster 1, the high-value frequent buyers who are the company's most important customers, who spend on average about £190. And then Cluster 2 consisted of regular mid-level buyers, forming a solid base of reliable shoppers who spend around £21,000. And then there's Clusters 0 and 3, represented by low-activity, low spenders, which is a large group of casual or one-time shoppers. And this helps the company understand who their customers are. Our market basket analysis, on the other hand, helped us understand what products are bought together. The key finding was that rules with very high lift values are extremely valuable. So for example, the rule linking the pink and green Regency teacups had a lift of almost 25, meaning they are bought together far more often than by random chance. So how do these insights work together? So the real power comes from combining these two insights, right? So the company can now move beyond generic marketing and create personalized campaigns. For instance, they can offer special product bundles. So these are identified from association rules, specifically to their high-value customers from Cluster 1. Now, they can encourage mid-level buyers to spend more by suggesting related items and re-engage low-activity shoppers with deals on popular product pairs to entice them back. So, in conclusion, this project successfully explored customer behavior using clustering and association rule mining. So we segmented customers into meaningful groups, extracted actionable rules about product co-purchases, and conceptually designed a feature reinforcement learning system. The main takeaway is that clustering helps understand customer diversity, association rules reveal shopping patterns, and reinforcement learning holds promise for automating complex decisions. Now, based on our findings, we offer these following recommendations. First, for customer segments, we recommend to implement segment-specific marketing, such as offering bulk discounts to volume buyers, and create loyalty campaigns to retain your high-value customers. And then for association rules, we use the strong product pairings we found to create product bundles to improve online recommendation system and even optimize the layout of a physical store. And then for future reinforcement learning integration, we recommend exploring the use of reinforcement learning to create smart recommendation agents, dynamically time promotions for maximum impact, and chain agents to optimize inventory management, reducing both overstock and shortages. And we believe by implementing these data-driven strategies, the company can enhance customer experience, increase sales, and operate more efficiently. So this concludes my presentation. Thank you for your time, sir.